Good day, this is Jim Pytel from Columbia Gorge Community College. This is Digital Electronics 1. This lecture is entitled Multiplexers and Demultiplexers. Multiplexers and demultiplexers are common functions combinational logic, and their purpose is to kind of be the traffic cops or the postman of digital logic. And the best way to describe them is using their schematic symbols. And sometimes you're going to see different symbols. For some reason, people don't use these symbols all the time. But think about here's a multiplexer. It's taking parallel information, routing them onto a single serial line. And if you look at the schematic, it's like a funnel, okay? And it's a great description of how a multiplexer works. Same thing with a demultiplexer. You've got incoming serial data, and it's expanding out into parallel data. So what they are is parallel to serial converters for a multiplexer. In the case of a demultiplexer, it's a serial to parallel converter. Another apt description for a multiplexer or demultiplexer, it's a switch. And what's really neat about it, it's a switch with no moving parts. Multiplexers and demultiplexers are actually kind of my favorite common function of combinational logic. And the reason why they're my favorite is it's my first, when I went back, way back when I did this thing, it was one of the first devices I created on a transistor level. I didn't use logic gates. I actually used the transistors to create these things. And it was really cool to see, okay, this is switching this input to that output. And there's no moving parts. Very similar to the thyristors and SCRs, which I'm going to talk your ears off about in later classes. Those things are replacing a mechanical relay, with movable contacts. The SCR and thyristor, it's no moving parts. The multiplexer, same thing. It's a switch without any moving parts. Key to understanding the multiplexer and demultiplexer is your Boolean rules. And there's only two you need to understand, is A and 1 is always equal to A. A and 0 is always equal to 0. So understanding those Boolean rules is key to the behavior of both these devices. What that means is this signal right here, either placing a 1 on it or a 0 on it, acts as an enable, go through or don't go through. And that's kind of the traffic cop analogy. You think about it, you got a intersection with like 4 roads coming into it. This dude in the middle of the intersection is telling you, okay, you go down that single one-way road. Now you go down that single one-way road. And that's exactly what that enable signal is going. So let's go ahead and draw a graphic of what I'm talking about with these Boolean rules. Okay, so here's Johnny AND gate, and it's got incoming digital data, A, on one of its inputs, and its secondary input here, we're going to go ahead and just place a 1 on it. So what happens to the output? Well, it looks exactly like A. Now we go ahead and replace that secondary input. We go ahead and put a 0 on it. Regardless of what's happening to A, what happens is our output? Nothing. Okay, 0, straight 0. That secondary input is acting like an enable. Let's extend this ever so slightly by adding another AND gate. And then what we'll do is with this secondary AND gate, we're going to go ahead and do something funky with its inputs. Let's go ahead and just put a B input on one of its inputs. There you go. And then let's go ahead and that enable area, kind of that secondary input to the first multiplexer, first AND gate. I'm going to call that an enable, or let's call it a select. And what I'm going to do is feed that select to the second AND gate, but invert it. And I like teaching multiplexers in this fashion here. Think of colored inputs. A is red and it's got a certain duty cycle, and B is blue and it's got a certain duty cycle. Make use of this Boolean rules here and see what happens on those outputs. If I go ahead and not tie them together, because you never tie outputs together, put an OR gate between them where this is the output X. What are the properties of an OR gate? A OR 0 is A. Okay, that's the central property to understand this circuit here. So we went from a single AND gate, now we've got 2 AND gates with an inverter and an OR. It sounds like an SOP, okay, sum of products expression. When select is 1, that's a 1. That's a 0 there. This AND gate is enabled. It's A and 1. This AND gate has a 0 output regardless because we are currently in this state right here. This AND gate is in that state. It's A and 1. What comes out is A. That colored input A with its duty cycle here. What is the OR gate doing? Well, it's A or 0. What comes out is A. It's looking exactly the the same as A. Now, check this out. The select input goes to 0. Now what happens? Let me go ahead and clean it up. Okay, so when the select input goes to 0, the first AND gate gets a 0 on one of its inputs. Regardless of what A is, A and 0 is 0. Okay, that AND gate is disabled. What happens to the second AND gate? Well, it's getting select is inverted, so it gets a 1. I'm enabling the second AND gate. What do I get? B and 1 is equal to B. Okay, so the output of the first AND gate is 0. The output of the second AND gate is B. What do I get here at the final output for the OR? It's B or 0. Well, ultimately, I'm going to get B. And that's the whole idea of this traffic cop. That select signal is selecting which one gets through. In this particular configuration, when select is a 0, B is selected. When select is a 1, A is selected. And again, it's no moving parts. It's like a switch. When in our multiplexer schematic symbol, it's got two inputs here. It's got this select input, and it's got A and B data inputs. What's the output? X. When select is a 1, A comes through. When select is a 0, B comes through. And that's sometimes the kind of the schematic symbol you see. What are the inputs for our multiplexer? Well, it's data inputs and a select, okay, because it's got to select between which inputs it has. What is its output? It's a single output X. I'll go ahead and get rid of the definitions of A and B, and what I'll do is just say data 1, data 0. How many select data bits do I need? Well, I need 1 because there are 2 incoming data lines. Because when S0 is a 0, it's selecting D0. When S0 is a 1, it's selecting D1. What if I was to expand this to a 4 to 1? Okay, how many different select positions would I need to choose from 4 incoming data? And the answer is 2. It's binary. Think about it. 0, 0, 0, 1, 1, 0, 1, 1. So let's expand our multiplexer definition out into a 4 to 1 multiplexer. There's our 4 to 1 multiplexer. When S1, S0 is 0, 0, it selects D0. When it's 0, 1, it selects D1, D2, 1, 0, 1, 1. Again, that is from S1, S0. So I can kind of come up with a truth table. S1, S0. Those are my inputs. Well, what are my outputs? So let's all possible combinations, 0, 0, 0, 1, 1, 0, 1, 1. My output X, I could do all sorts of crazy truth tables with D0 being a 1 and a 0. Just say D0, D1, D2, D3. These are selecting from those individual inputs. And if you want to, and again, I know it's no moving parts, but if you could imagine when S1, S0 is 0, 0, there's a switch in there, hooking D0 to the output X. And like we showed in this previous analysis right here, it's all the other AND gates that are feeding that OR gate output are at 0, and the only one that's enabled happens to be at D0. When S1, S0 is at 0, 1, who is selected? D1. So it's that, just think of that moving switch analogy. So I gave you kind of the SOP expression up here for a 2 to 1. And a 2 to 1, the output X in our particular example right here is our select, let's just call it S. So S and A or S and B. In the case of when S is 0, B is active. So I've got to put a negation over it. So when S is 1, A gets through. When S is 0, B gets through. What would you think the SOP definition of the 4 to 1 multiplexer would be? Think about in terms of a circuit. Obviously, there are 4 inputs. I'm going to need 4 AND gates. So that 4 AND gate partial schematic symbol looks like this. I've got D3 being fed to one AND gate, D2 to another, D1 to another, D0 to another. And if I want to select, let's just the easiest one, D3 is the input. So D3, I'm talking about this guy right there, that top one. If I want D3 to come in, I want to enable that AND gate. And I want to go ahead and turn these other AND gates off, i.e. give them a 0, disable those. How do I enable D3 using just the S1, S0 inputs, the select inputs? Well, I gave you the easiest one. Make sure that AND gate has a 1 on it with S1, 1, S0, 1. Well, they're both 1s. Just go ahead and feed S1, S0 to that AND gate. And that AND gate is enabled. And I know I haven't drawn the other ones yet, because what I'm going to do is now go ahead and go to D2. When S1 is 1 and S0 is a 0, how do I make sure that this AND gate is enabled and all the other ones are off? Well, check this out. If S1 is a 1, just feed it S1. If S0 is a 0, I want this AND gate to have a 1, i.e. enable it. All I do is feed it not S0. And now you might, here, let me go ahead and redraw this here so you can see it. What happens in that case? When S1, S0 is 1, 0, what happens to this AND gate? Well, its expression is D3 ANDed with S1, ANDed with S0. Well, S1 is a 1, S0 is a 0, D3 could take whatever data value it has. What is anything ANDed with a 0? It's a 0. I'm disabling that AND gate. Whereas D2, what is the output for this AND gate? Well, it's D2 and S1 ANDed with not S0. When S0 is a 1, S1 is a 1, and S0 is a 0, not S0 is a 1. So 1 and 1 is a 1, and with D2, the output of that AND gate is D2. Okay, so D2 is coming through. It's pretty neat. What we do is we just go ahead and for that select position, the binary equivalent, very similar to our SOP expressions here, is, let's take the example, S1, S0, 0, 1. How do I enable that AND gate? Well, just invert S1. S0 is already a 0, so keep it a 0 and tie that input here. So not S1, S0. Move on to D0. Well, if it's 0, 0 on the select inputs, invert it, invert it. Go ahead and try those combinations. 0, 0. For example, 0, 0. Which one comes through? Well, D0 ANDed with not S1, ANDed with not S0 gives a D1 output, D0 output. What are the outputs of all the other AND gates when S1, S0 is 0, 0? Well, that one's a 0, that one's a 0, that one's a 0. What do I get for my OR gate? It's D0 or 0. I get D0 as my output. Move it over to S1, S0, 0, 1. That one has a 0 output, that one has a 0 output, that one has a 0 output. What's this one's output? It's D1. D1 or 0, D1. Okay, it's a switch. It's a switch without any moving parts. Just by giving that address for that data select, I'm capable of routing that parallel incoming data to a single serial line. So what is the SOP expression for, in this case, a 4-to-1 multiplexer? Should look something like this. There you go. X is equal to D3 and S1 and S0, because again, we got 1, 1 for our selects. D2 or D2 ANDed with S1, not S0, because again, it's 1, 0. And then or D1 ANDed with not S1, S0, because it's 0, 1. And finally, ORed with D0, not S1, not S0, because we're trying to select for position 0, 0. It's pretty cool. We've came up with an SOP expression for a 4-to-1 multiplexer. And what's really neat about the multiplexers and demultiplexer lectures, and kind of supporting exactly what we just went over in the adder lectures, we can do this in a structural approach. Okay, I know we just came up with an SOP expression for a 2-to-1 and an SOP expression for a 4-to-1. What I can do is expand these things. Go to an 8-to-1, go to a 16-to-1, go to a 32-to-1 using a structural approach. Okay, let's go ahead and I'm going to clean this up here and let's go back just to our 2-to-1. And what I'm trying to do is just closely parallel what I've done with it. Parallel binary adders. I'm making a component once and instantiating that several times. And this makes a great take-home exercise. Oh my gosh, it might even be a take-home exercise. So go ahead and look up the take-home exercises, and maybe you want to pay attention to what's going on here, and maybe you want to review some of those lectures which we've already gone over with the structural approach for an adders to help you out. Let's go ahead and look at a 2-to-1 multiplexer. So our basic 2-to-1 multiplexer here has got 3 inputs. Let's call this D0, D1, and S. And then when S is 0, D0 gets through. When S is 1, D1 gets through. And I know I flip-flop the order of the MSB to LSB on that last one. Just be aware of it. I'm just saying now the LSB is at the top. It doesn't matter. I can draw it the other way if I wanted to too. The behavior of that 2-to-1 multiplexer should be pretty easy to understand. How can I use 2-to-1 multiplexer to create a 4-to-1 multiplexer? And think about a bunch of highways, 4 highways coming in, and what I want to do is have 1 highway coming out. And if I had to use 2-to-1 multiplexer, what I could do is use a 2-to-1 multiplexer at the output to pick from either the north half or the south half, okay? So what that means is potentially I could use a multiplexer on each one of those. So there's the north half and the south half, and those multiplexers could choose respectively the north half or the south half on their respective highways. Okay, so you see what I've done here is I've taken 1 2-to-1 multiplexer, 2 2-to-1 multiplexers, 3 2-to-1 multiplexers, put it in a big trapezoidal shaped box, and I've come up with 4-to-1 multiplexer. What are the input positions? Well, S1, S0, where do they go? Well, let's just say that is the MSB. I can tie S1 to that one and S0 to that one. If in the particular case where that's 0, 1, 0, 1, 0, 1, and S0 is a 0. Who gets onto the highway? Let's get rid of all these colored things. Okay, when S0 is a 0, that data position is being routed onto that one. When S0 is a 0, that is being routed onto this one. Now this second this second level of multiplexer, i.e. this one right here, now chooses using the S1 bit. And let's say the S1 bit is 1. Which one does it choose? It chooses this guy right here. So it's taking that 1, 0 position, respectively. D0, D1, D2, and D3. Okay, let's do another example of that because that might be confusing. Okay, so here's a prettified version. We've got 3 2-to-1 multiplexers, and this first level of multiplexers are all being fed the same S signal. Let's call that S0. And then this one is being fed S1. Where does the output of that first multiplexer and the second multiplexer go? It goes to that second level multiplexer. So now let's go ahead and say S0 equals 0, S1 equals 0. Which one does it select? Well, this one and this one. And finally, S1, which one does it select? It selects this path. So who gets through? D0. We can just as easily put this in a timing diagram. It looking something like this. Okay, and here is a pretty comical example here, and the reason why it's comical, and I know this seems kind of stupid to do it this way, but trust me, you'll understand what I'm talking about here when you look at the digital data streams. Is D3, D2, D1, and D0, are they really truly logical values? No, I've purposely drawn them as weird waveforms. Additionally, notice I've used different colors. And the reason why I'm doing this, I know it's not valid logical data. What I'm trying to do is just show you when the select positions are such that D0 comes through. What comes through is D0's representation. D0 could be a digital logic value going 0 to 1, but just look what happens here is in this position, S0, 0, S1, 0. Who gets there? Well, D0. So just think about from here to here, it's going to ignore all the other data inputs and it's going to put in D0. What does D0 look like? Well, it's this green noise. Now, when it goes to select S10, S01, who is being enabled? Let's go back to our example here. When it's S1 is 0, S0 is 1, who gets selected? Well, all the ones get selected for the lower. And then finally, this one passes through that. So we're getting D1. So as a reminder, you just say D1 from here to there. What's D1? Well, it's this gray triangular wave, and I'm going to try to match what it looks like. It kind of looks something like this. I know I'm slightly off. Next, it's going to be S11, S00, 1, 0. Go ahead and redo our diagram. Okay, so who is switched on for the lower orders? Well, all the ones connected to a 0. All the ones connected to a 0. For our high order, who is selected on? All the ones with a 1. And what do we get as our output? It's D2. What does D2 in this comical example look like? It looks like a ramp wave. And I'm going to try to do it justice like that. Finally, so we've run out of options here. What's this? It's obviously D3 because I've got 1, 1, 1, 1 on my select inputs. And according to our little diagram here, what do I get? It's 1, 1. Who gets there? D3. What does D3 look like? It's this turquoise sine wave. Now, I hopefully understood what I'm talking about here with these comical examples of waveforms, but now just put digital data on D0. Put digital data, whatever data stream it represents, on D1, D2, D3, and go ahead and do the exact same analysis. And there you go. There's digital data on inputs D0 through D3. I have not changed the select inputs. And if that's the case, if I have not changed the select inputs, my output from here to here should be D0. What does D0 look like in this window? Well, it's routing, something that looks kind of like that. What is D1 for this window? Something that looks kind of like this. What is, you get the picture, D2 for that window. What's D3 for that window? Your picture should look something like this. There you go. If this S1, S0 is kind of this timing, it's a clock. It's going from 0, 0 to 0, 1. Excuse me, it's a counter. It's going from 0, 0 to 0, 1 to 1, 0 to 1, 1. What I'm doing is basically this time division multiplexing. All those inputs, D0, D1, D2, D3, get time portion use of that particular serial passageway. Okay, in this particular case, since there are a lot of time, equal time implements, it's just going to go in this cycle D0, D1, D2, D3, back to D0. So on and so forth. But understand that I could have any arrangement of those S1, S0s. Hopefully you understood the example problem here. And the point is not only did I introduce the timing diagrams with the multiplexer, is this concept here of a structural definition of a 4-to-1 multiplexer using 3 2-to-1 multiplexers. What do you think this would look like in VHDL? Because I'm going to ask you to do this again for one of your take-home assignments. Here, what does my output look like? I want to create a 4-to-1 multiplexer that looks like this. It has 4 inputs, 4 data inputs, 2 select inputs, 1 data output. When I make a 4-to-1 multiplexer using 3 2-to-1 multiplexers, how many components am I using? Trick question. How many instantiations of components am I using? Are there any internal signals that I might need to declare? Okay, so think about that. What I'm referring to is obviously this picture right here. How would I do a port map to those component instantiations? Again, potentially using internal signals. So think about that. Because what I'm doing is I'm going to throw something at you. The multiplexers and demultiplexers are an excellent way to introduce these behavioral descriptions. Okay, we've already gone over a data flow description of a 2-to-1 multiplexer. Let's go back to our definition of a 2-to-1 multiplexer. Let's see if we can find a blank spot. Okay, this one should be easy. What is the data flow or the SOP expression for that 2-to-1 multiplexer? We've got 3 inputs, D0, D1, and S. What I want X to be assigned, well, in this case, let's just use the SOP expression. When S is a 1, I want D1 through, or D0, not S. Okay, so that is an SOP expression. That's kind of the data flow version of VHDL. And I know I haven't written in VHDL syntax. You should be able to do that. Now, I want you to, obviously I'm going to have you do the structural using 3 2-to-1 multiplexers to create a 4-to-1 multiplexer. There's another way I could describe the behavior of that particular 2-to-1 multiplexer. And that's what's known as a behavioral description within VHDL. I can use that 2-to-1 multiplexer in either data flow mode or a behavioral description as a structural component. Okay, it doesn't matter how I describe it, whether an SOP expression or one of the behaviorals that I'll give you guys. Okay, the 3 behavioral methods we're going to use is this concept of an if process, a when, and hopefully we'll be able to get to a case. So what I can do, and I know I haven't introduced how to use the if, whens, and case, what I could do is define a 2-to-1 multiplexer using the if process, and then use that in a structural method to form a 4-to-1 multiplexer. So I don't necessarily always need to use data flow, whereas previously in our half adder, we had a data flow core. What we're going to try to do for this take-home exercise here is use any one of the behavioral definitions, what I'm about to show you here, use that as a core for your 2-to-1 multiplexer, and then use it in a structural approach. So I'm combining now behavioral and structural as opposed to data flow and structural. And with behavioral, if you remember right, we did that truth table in Unit 5, entering a truth table in VHDL using that select assignment. So that's kind of we could do that too. Behavioral methods are pretty cool. They're kind of like one of those hand grenades you throw into a room of bad guys. It's you don't care how it's done as long as it's done, as opposed to a data flow as I am coming up with the expression which I specifically want you to go ahead and do. Behavioral is what you're kind of do is setting up your inputs. Here are my inputs. When this input is happening, I want that output to behave this way. So let's do the if and when first. Might get back to the case a little bit later. We've already gone over the select. So let's try an if. Okay, so here is our VHDL program. We've got our library, which is not on the screen. We've got our entity. I'm not going to do it because you should be able to easily come up with an entity description for our 2-to-1 multiplexer. And then we got our architecture. What I'm calling it is behavioral if of our mux 2-to-1 is begin. Obviously, that's something you've already seen before. What am I going to put in begin? Well, I'm not going to put the SOP expression. However, if I did put the SOP expression, it would look something like this. Okay, assuming I've defined my inputs and outputs like that. So what I'm going to do is kind of come up with something that does the exact same thing using the if statement. And like I said, it's a process. It's different than those concurrent assignments which we've been talking about. Remember those internal signals? I can do M is this, N is that, and the final output is X equals M or N. I could just as easily do it opposite. X is equal to M or N, and then assigning M or N because it's concurrent. Okay, it's happening simultaneously. The process is procedural or sequential. It's executed in sequence. Okay, so I have to kind of tell it I'm going to use a process. It's one of those keywords, but I got to come up with a name for it. Process 1 : process. What it's got is these inputs. It's got a sensitivity list. Sensitivity list, what makes it tick? Well, obviously it's got D0, it's got D1, and it's got S, okay? So it's just kind of, that's what's known as a sensitivity. You know, what makes it do something? Because obviously when D0 changes, S changes, or D1 changes, it's gonna do something, okay? I've got to begin that process. So I'm within that process. That's why I'm gonna indent it again, okay? So I'm knowing where I'm at. Obviously it's an if. If, in this particular case, S is logical value 0, then what I'm going to do is it's just going to say X is assigned D0. It's kind of like that expression D0 not S, and obviously we're going to have D1 S. So I've got to come up with the second portion of it. So that what I've just done is I've described this using that right there. Now I've got to come up with the description for this guy. All I'm going to do is going to say else, okay, because I've only got 2 choices. Else, let me give myself some room. I'm going to go else, X is assigned D1, semicolon. Now I've got to go ahead and end that if, and finally I've got to end that process, semicolon. And notice how I've indented that, and that's kind of like a layer within a layer within a layer. I'm just kind of telling myself exactly what's going on. And it's making that exact same decision like our SOP expression, which we've got over here. When S is a 0, the output is D0. When S is a 1, i.e. else, our output is D1. So it's pretty cool. I don't even care about the SOP expression. I just tossed a hand grenade into here and boom, all of a sudden it came out exactly the way I want it to happen. It's a behavioral description. I don't care how this FPGA and the software utility executes this thing. Just do what I tell you to. There's an alternative, especially when you've got something very, very simple like this here, using a when, whereas the if statement has to be within that process statement. I can just as easily do a when definition. So let's go ahead and erase what I've got here, and you can put a when definition kind of all in one line. Okay, so here I am. I'm still within the begin of the architecture. Oh, geez, I gotta erase everything. Good thing I checked. I'm still within the begin of the architecture. What I'm going to do is say X is assigned D0 when S is equal to 0, else D1. Okay, so it's an alternative. Oh, geez, let me spell else correctly. So it's making that decision. It's just a behavioral high level. I don't care how you do it. Do this. When S is 0, make it D0. Else, make X equal to D1. So it's pretty cool. Very quick, very snappy, one line behavioral description. And I could call that description behavioral when. So you got 2 new tools in your bag there. You get the if statement, which is a part of a process, and then you've got the when statement, which doesn't necessarily need to be within that process sub menu there. And we've also got that data flow description. So you should be able to using some of the structural techniques which we discussed in our adder lectures, just go ahead and make a behavioral core for this guy, and then hook it up in a structural manner to create our 4-to-1 multiplexers. So let's continue with some discussion of multiplexers potentially hooked up in a different fashion, making use of a single serial line. Okay, consider, if you will, this arrangement of 2-to-1 multiplexers. This is what's known as a quad 2-to-1 multiplexer. What's quad? It's four 2-to-1 multiplexers. These things are especially handy when we go into display multiplexing. And what display multiplexing is, one of the definitions of display multiplexing is using a single driver to display 2 different numbers or 4 different numbers or 16 different numbers on 16 different displays, okay? And what you're trying to do is basically, in this particular example, we're going to select between 2 numbers. Let's just call it A and B. What I'm going to do, and they're BCD numbers. Let's just say that's A3. Let's use different colors here. So I put my A number, MSB to LSB, going down that direction, on the 0 input. And I'll take my B number, my BCD, it's a 4-bit binary code, put it on the same inputs. When S is a 0, what gets through? A. When S is a 1, what gets through? Obviously B. There you go. Okay, so it's pretty neat. I'm using that select on 4 separate 2-to-1 multiplexers to route a BCD number potentially to a display driver. So think of a 7447 BCD to 7-segment display driver. And here is my DCBA, MSB to LSB, my basically my 8, 4, 2, 1 weighted inputs for my BCD in. What do I have my outputs is A through G for my 7-segment display. And since I want to display 2 numbers, this is kind of cool. I want to display 2 numbers. I want to display B on this one and A on that one. Let's say, for example, 23. I want to display the number 23. First off, figure out what's on A, what's on B. So 23, I want to display 2, 3. I don't want to display 3, 2. I want to display 2, 3. So what's B's inputs? Well, it's 0, 0, 1, 0, 2. What's A's inputs? 0, 0, 1, 1. What's really cool about this is I can use this single BCD to 7-segment display driver to drive both of these 7-segment displays. And the key is doing it super, super fast. And what I'm going to do is when I'm displaying 20, I'm going to turn on this one and I'm going to turn off the other one, okay? And then when I display 3, I'm going to turn on this one and turn off the other one. And what I'm going to do is I'm going to go super fast. 2, 3, 2, 3, 2, 3. And what your eyes see is 23. And if you see 32, you've routed something wrong. So let's go ahead and see what we can do here. Okay, first thing is where do the output for those multiplexers go? Well, they just go to the BCD inputs for that particular 7447 display driver. There you go. I'm just routing the LSB position to the 1 weighted all the way up to the MSB to the 8 weighted. And you might think, well, hey, don't I have 2 outputs? I'm taking A3 and B3 simultaneously. No, it's selecting between them. The multiplexer is making that selection for you. Now, when, in this particular case, we've got when S is a 0, it's selecting for A. So what we need to do is enable the least significant display, the LSD. Yeah, don't use that term. I want to enable that display. When S is a 1, I want to enable the MSD, the most significant display. Yeah, I just invented 2 terms. Don't ever use them. So think about how I could potentially do that. I just turn on the anode when it's enabled. Turn off the anode when it's disabled. And what's neat here is, let's say for the example of S is 1, okay? It's selecting the B inputs. What I have is 20. What does 2 look like? A is on, B is on, C is off, D is on, E is on, F is off, G is on. It's a common anode display, CA. It takes a 0 to turn on. So A should have a 0, B should have a 0, C should have a 1, D 0, E 0, F 1, G 0. So what do my outputs look like? A through G. Okay, there's my outputs for that particular display of 2. A0, B0, C1, D0, E0, F1, G0. When I'm sending that data to this 7-segment display, I should see it lit up as a 2. But be aware, I'm sending that same 7-segment data to, and I'm not going to draw all the wires, to this display right here. The deal is I'm just not enabling that one's anode. How would I make the decision? Well, why not just use what we've already got right here? That S signal. How do I enable the anode for just B and not A? Well, just think about a transistor. You're working with a semiconductor devices and circuits. I could potentially use an NPN or a PNP transistor to, and again, in my world, just think about it. It's a switch. Depending on a PNP or NPN, whichever one you use. If you send it a 0, it'll be open. If you send it a 1, it'll be closed, and vice versa for the opposite. All you do is take that anode plus 5 volts and put a switch that opens or closes based upon this decision right here, that S description. So in the case of if S is 1, we want a 1 to close that switch, and obviously open the other switch. Why not just put in an inverter on that same S signal that is connecting or disconnecting that anode? And now let's go ahead and say S goes to 0. When S goes to 0, what data is being routed onto those BCD inputs? Well, it's 0, 0, 1, 1. This switch opens up, disabling the B segment display, i.e. this one, and because I'm inverting that signal 0 to a 1, I'm connecting this one's anode, and A turns on. What do I get? I should get the number 3, which is A, B, C, D, and F. Do that super fast. 2, 3, 2, 3. Pretty cool. It's display multiplexing. We're probably actually going to go into a bunch of display multiplexing, especially for the use of our FPGA development boards. It uses slightly different methodology, but very similar. It's all those 7-segment inputs are being sent to every single 7-segment display. It's just that I'm enabling the anode at a specific moment or disabling an anode at a specific moment. And again, you do this fast enough, you should be able to see a display without flicker. Flashing, well, not flashing. You should see the number 23. Pretty cool application of a multiplexer. Okay, let's talk about 2 specific fixed function integrated circuits, namely the 74157 and the 74151. They're both multiplexers, and what we're going to do is just show you how they're hooked up and basically apply what we've just done. Okay, so here's the pinout for 74157 here. 16 pins. Obviously, you've got a VCC and a ground, and it's not exactly the easiest thing to read how this thing works. And I compare and contrast to the ANSI IEEE logic symbol, which I'll show you in a second here, as opposed to the pin diagram. It's got a select here, which is the data select. It's common to every single one of them. S, that's his data select. It's exactly what we just did there as a quad 2-to-1 multiplexer. It's selecting between the A input and the B input. So I'm taking my A's here and my B's there. What are my outputs? Well, look at this guy right here. 1A, 1B has the output 1Y. So here's my outputs. 1Y. There's 2A, 2B, 2Y, 3A, 3B, 3Y, 4A, 4B, obviously 4Y. How do I know that? Well, because I've used this thing a lot, and I know what it's working, how it's wired up. But the pin diagram doesn't really show you that. You'd have to look into the data sheet for it. However, you can also use the ANSI IEEE logic symbol, and it's neat because it's got this common control. And one last thing I forgot before I go into that, it's this enable, and notice it's got a low bar over it, basically a negation bar over it. For this thing to work at all, that enable has to be tied to ground or given a logical 0. So I can turn the thing on or I can turn the thing off, potentially even using 2 of these guys in combination to route 4 separate BCD numbers to a single display. Okay, so let's talk about the ANSI IEEE logic symbol, and I'll put that up here. And what's really cool about the ANSI IEEE logic symbol is you know how it works just at a glance. Okay, I'll show you what I'm talking about. So here's the ANSI IEEE logic symbol for the same 74157. What's really neat, it's got this thing at the top here, there's kind of this weird funky shaped block there. That's what's known as the common control block. Okay, and what that is basically that includes all the inputs common to the devices below it. So what it's saying enable. Okay, it's got to be low. It's got that flag symbol on it for the whole thing to work. It's got a data select G1, which is this control there. That's what's controlling the behavior of those things. Every single one of those guys gets those enable inputs and G1 inputs. And you can instantly see using this ANSI IEEE logic symbol, okay, I got 4, 1, 2, 3, 4, 2 to 1 multiplexers. And you know which those pins, and by the way, there are pin numbers on this thing too, like that. It has a little parentheses 2, parentheses 3, all the way, so on and so forth, to match this thing. So in addition to the pin numbers, which you'd get from like the pinout diagram, using this definition, you get to see how the thing works. So it's pretty cool. The ability to use the ANSI IEEE logic symbol, it kind of shortens your data sheet. It's the symbol itself is a data sheet. That was the 74157 quad 2-input data selector multiplexer. Data selector is the same. It's the same name. Let's go into a 74151, and that is an 8 to 1 multiplexer. Now think about it, 8 to 1. How many select inputs should I have? 8 to 1. And what we're going to use is we're going to use this in a data selector application. And this is really cool because you can see using it in a data selector input application, we can create a combinational logic circuit in the form of a lookup table. Okay, so let's go over the 74151. Okay, so the 74151, like I said, it's an 8 to 1 multiplexer. If you look at the data sheet for this one, you look up at the ANSI IEEE logic symbol, there is no common control common control block because it's one multiplexer. All inputs control this multiplexer. 8 to 1, obviously it has 3 select positions, S2, S1, S0. Why is it 3? Well, 2 to the third is equal to 8. You need to have 3 bits to control 8 potential inputs. So what I'm going to do is those are my selects, S2, S1, S0. When it's, let's do it, MSB to LSB, 111 all the way to 000. Additionally, there is an active low enable and obviously an output Y. And just because we got to keep the pins even, there's also a not Y output. It's obviously the inversion of Y. Before we go into this as a data select application, this active low enable is pretty key. And it's because there are 3 data select lines that active low enable is key. One would think, let's say, for example, we're using the counter application. 000 goes to 001, 010, 011, so on and so forth, going from the possibilities of D0 all the way up to D7. And let's say everybody gets an equal share for a little bit of time and then comes back, and then you break it out, apportion it out to 1/8 of whatever that time cycle was. One would think that there's this clean and even transition from 000 to 001, and this super clean, snappy transition from 001 to 010. And that's a good transition to talk about, 001. Let's just draw a timing diagram here so you can see what I'm talking about. Okay, so it's 001 on S2. Oh, I'm doing this backwards. Sorry, let me redo that. Okay, so I've got 001. Ignore the enable for a moment. And one would expect that snappy transition to 2 to be instantaneous, simultaneous, with no overlap. You expect it to cleanly transition from position D1 to instantly selecting for D2. I'm here to tell you it doesn't happen that way all the time because, say for example, the LSB thing changes, the LSB position changes first, and then like this one changes first. Notice the gap there before S2 changes. What am I reading right here? It's 000. It's a glitch. So how can I potentially use the enable to avoid that glitch? Well, it's an active low enable. What I would do is I would enable it when it's 001, disable it during that glitch period, enable it when all those inputs have settled down, disable it during a transition, for example, to 3, because there may be a glitch there. So I'm going to disable it, enable it, i.e. give it a low. Those are all when it's enabled, when those inputs have stabilized. So what I'm doing is I'm turning it off when those inputs are wiggling around, still trying to figure out what's going on. And then when they're stabilized, boom, enable it. Okay, it's called strobing. Think about a strobe light. Someone moving around in a strobe light. It looks like they're suddenly transitioning from position to position. That's all I'm doing. I'm strobing it. Okay, active low. Take that inputs now. Okay, they're still trying to shuffle their seats. Just ignore it. Okay, they're in their seats. Take that. They're shuffling around. Ignore it. Okay, they're in their seats. Go ahead and take that data. Okay, so that's a pretty cool application of the enable. but I digress. Let's talk about the data selection function. If we remember right, we came up with a combinational logic function, and I cannot believe we're going back to it, the Happy Cat cat food factory, based off of 3 inputs: seals, husks, and mats. And we came up with an output X. With 3 inputs, 3 binary inputs, I should come up with a truth table having 8 values. So what does that truth table look like? Like this. We came up with an SOP expression from that truth table with cat food is equal to seals and husks, or seals and mats, an SOP expression. How many gates does it take you to do that? Well, it's an SOP expression with 2 product terms. Sounds like it's an AND gate, with an AND gate being ORed together based off 3 inputs: S, H, S, M, and S obviously being tied together because it's the same input. So 1 gate, 2 gates, 3 gates. I would have to grab a 7408, 7432, but check it out, 3 inputs. 3 inputs. Why not just make the selects my inputs S, H, and M? Why not take D0 through D7, tie them to an appropriate logical high or logical low? This represents 000. Who gets 000? Well, D0. Why not put a 0 on there? Basically hardwire it to ground. D1 gets a 0. D2, D3, D4, get up to D5. Put a 1 there. Put a 1 there. Put a 1 there. What I've created is, in effect, a lookup table. How many fixed function devices have I used? I've used 174, 151. Pretty neat, huh? So rather than using 2 fixed function devices to implement an SOP expression, I use 1 common function of combinational logic, i.e. the multiplexer, in this case an 8-to-1, to implement exactly the same SOP expression. And obviously I've got to tie my enable to low, and when I give it seal input 1, husks input 1, mats input 0. What am I selecting? I'm selecting that one. 110. It's this one. Who gets selected using our switch analogy? It outputs a 1. And this is exactly what a field programmable gate array is doing. In contrast to a CPLD, the generation previous, the programmable logic device previous to the FPGA, it really did implement the SOP expression. Whereas a field programmable gate array, it uses memory, which you created using your VHDL expressions, and you came up with it. It basically takes the output of that SOP expression and puts it into memory. Then it uses a data selector. I know it's not using a 74151. It's using a data selector, and these are your inputs. And all it does is just route the appropriate memory position, in this case, this one, to the output. If those inputs change, it does that data selector to a different location within your memory. This is a super cool application. I've saved myself, if I'm using fixed function, I'm saving myself potentially 2 physical devices that need to be wired up, and in the case of like a mobile application for a really small device, I'm saving some weight and some power consumption when I could just use one of these things. Pretty neat. It's a lookup table using data selection. Okay, so on the other end of this whole multiplex arrangement, which we haven't really even discussed yet, is this demultiplexer. And exactly like the multiplexer being a parallel to serial converter, what's a demultiplexer? It's a serial to parallel converter. And it's got 1 input, i.e. the serial input, several parallel outputs, and select input to determine which one of those receiver outputs it's assigned to. And then if you want to think about it in terms of a switch, in the case of a multiplexer, when our S0 is a 1, it's selecting D1. When our S0 is a 1, it's selecting receiver 1. Okay, so here is our in. That is an in. That is an out. That is an out. Whereas this one's an in, out. Okay, so the S's are always in. The select positions are always in. Whereas a multiplexer is taking parallel, making serial. Demultiplexer is serial, making parallel. And that's this arrangement of which I've created right here, it's a multiplexer feeding a demultiplexer. That's exactly what they're used for. Is, let's say you've got your company in, I don't know, like Portland, Oregon, and you got a company in the Dalles, Oregon, and you got a single wire, and you're trying to send from computer system D1 or D0 to receiver 1, receiver 0, and you get that single wire. Well, actually, you're going to have 2 wires because you have to tie the selects together. There are other ways of doing that, but for this simple application here, when S0 equals 1, okay, it is selecting the input from D1 to go onto the serial line, and then it's selecting from that serial line to go to receiver 1. So the demultiplexer is exactly the opposite of a multiplexer. If you want to go ahead and think of it again in the gate level, for an AND gate to be enabled, what I'm going to do is I'm going to put the input on every single AND gate. Basically, I'm going to put the serial input on every single AND gate. And then for that receiver, for that particular receiver, I'm just going to put the selects such that that AND gate is enabled. Okay, I'll go ahead and draw exactly what I'm talking about. Okay, so there's two AND gates. I've got my input, let's just call that X. The output of the multiplexer is the input of the demultiplexer. So there's my input X. It's a digital data signal. It's got data on it. It can form whatever zeros or ones. And what I want to do is use that select position. In this particular case, we only have one select bit because can choose from one of two. What I'm going to do is tie, so S0. When S0 is 1, which AND gate is enabled? The top one here. Because what I get is 1 and X equals X. What is the bottom AND gate? Well, if S0 is a 1, it's inverted to a 0. What do I get is 0 and X, 0. So R0 is getting 0. Now, when S0 is getting a 0, what happens? I'm disabling the top AND gate. So this one kind of turns off, doesn't turn off, it just goes to 0. I got a 1 right there. What I get is 1 and X, X. Okay, and this is kind of the postman analogy. It's reading the address, delivering that incoming data, which is the X, to the appropriate receiver, the address. And again, what am I using? I'm using ands and nuts. And I can expand this out to do a 4 to 1, I expand that out to do an 8 to 1, 16 to 1, or excuse me, 1 to 4, 1 to 8, 1 to 16. So again, we are going from serial and expanding out into parallel based upon that address information for S0, S1, S2, so on and so forth. Okay, this concludes our discussion of multiplexers and demultiplexers. And along the way, I've tricked you into learning the difference between a data flow core and a behavior core using the if and when. We'll try to get back to the case statement a little bit later. And if you understand a 2 to 1 multiplexer, you should be able to make a 4 to 1 multiplexer using a 2 to 1 structural. You should be able to make an 8 to 1. Potentially, you should be able to use the behavioral core for that 2 to 1 and instantiate it as a component. We discussed applications of display multiplexing and the data selector lookup table, and we discussed a multiplexer and demultiplexer, obviously sharing that same line. And the key thing is just that understanding of a traffic cop or the post office mentality. It's got an address, there's a sender, and then a receiver. Let's move on to some further combinational logic functions.